All right, happy Monday. How's it going? So I'm spacey and grumpy, but we'll get through it. So exam 1 is tomorrow. So post it on Canvas, practice exams, review worksheets, and the solutions to those. And the other thing that's up there is equations and constants, just to make sure everybody understands. Those equations and constants are exactly what you'll be provided with. So that's what not to write on your legal cheat sheet. Okay? All right. I think I've handed out pretty much all of graded homeworks 1 through 3. If you don't have yours, come up after class. Homework 5 is currently posted on Canvas, a little bit shorter, partly because we have exam this week. But the first 3 questions, first 2 problems are relevant to the exam. Then the exam is in 12:10 LeBaron tomorrow, unless you're taking one of the alternative times, in which case make sure you read your emails. 6:45 is the official start, but we get the room from 6:30 on. So if you're there and seated at 6:30, 6:35, we'll get you started, and we'll go until as close to 8 as we can, because I don't know when the next people come in. Right? The exam's not written to take that entire time, but I also don't want time pressure to be a factor in your performance. All right? So if you show up early, we'll get started early. And then the way this is going to work, because we have an evening exam, I have to give you an optional lecture time. So Friday's lecture, what's going to be optional, the homework's due on Friday, but you can turn it in on Thursday. Just drop it off at my office. All right? And then on Friday, that will be your opportunity to look over the exams that were graded. And then I believe that you're going to be covering for me on Friday. So that's also your opportunity to go through the exam with Brian. Yeah. Yeah, so the other opportunities will be during office hours the following week. Okay? Make sense? All right. What else? Whoops. It's going to be that. It's been that kind of a day. There we go. I've got to fix this. Fit to size. There we go. All right, so sort of an overview of what we've been talking about. So putting things in perspective. Chapter 1, we talked about particles and their quantized energy levels. That is, the permissible energy levels. We know that systems are made of those particles. So if I have systems that consist of particles with quantized energy levels, that means my overall system has quantized energy level. And that means that I can think of a system as existing in a particular quantum state. All right. Then what we're going to do is we're going to say, all right, we want to know the average over a whole mess of possible quantum states. So we constructed this idea of an ensemble where I have lots and lots of systems, all with the same number of particles, all with the same volume, and all with the same temperature. And what we expect is that they're going to be distributed over many different quantum states. But if I take the average of this ensemble, looking at pressure or enthalpy or whatever thermodynamic property we're interested in, if I take the average of the ensemble, that's what I expect to observe macroscopically on a day-to-day basis. All right? So we're going to be applying statistics to these systems in our ensemble. So previously what we've done is we've introduced the Boltzmann factor. What we've said is one of our systems in a particular quantum state has a probability of, or I should say, our systems have a probability of being in a particular quantum state that's given by the Boltzmann factor. And that's the exponential of minus beta times the energy of that quantum state, or knowing that beta is 1 over kBt, it's going to be the exponential of the energy reference to kBt. So we saw where that came from last time. Once we know that that's our proportionality to the probability of being in a particular quantum state, then we can define the probability using our normalization condition. And what we found is that the summation of the Boltzmann factors gives us what we're defining as the partition function. and that partition function is the reciprocal of the normalization constant. Okay? All right. And then the last time we met, we started with our statistics and said, well, if I know the definition of our partition function and relate it to the probability of our system being in a particular quantum state, we have this probability. If I know the energy of that state, I can multiply over all of the quantum states' energies times their probabilities. That summation will give me the average for our ensemble. And what we showed using a mathematical trick is that I can manipulate the partition function to get the average energy. So the partial of the natural log of the partition function with respect to beta is going to be gives us the negative of the average energy of the ensemble. All right? So we did that last time. All right, so what are we going to do today? What we're going to do today is we're going to introduce analytical expressions for the partition function. All right? So parts of them we will show where they come from later in this chapter, and then others we will derive in the following chapter. For right now, we're just going to say, here's a partition function. How can I use it to calculate the energy? All right? And then the question is, the energy of the ensemble, what does that tell us from a practical point of view? And we will explore that. The other thing I want to just mention at the outset, we have defined this system partition function as the capital Q. All right? We will see that, and this should make total sense, I have a system that consists of particles. So I have particles that have partition functions associated with them. So we call those the molecular or the particle partition function. To distinguish the two, we write that as a small q. Okay? All right? And so what we'll see is that we can use the system partition functions to determine, or the particle partition functions to determine the overall system partition function. Okay? Make sense? All right, so where we left last time was we showed explicitly that the energy of our ensemble is given by the partial of the natural log of the partition function of the system with respect to beta. Right? So we also are interested in having this in terms of temperature. So I want to take a moment to define it in terms of temperature. All right, so what I can say at the outset is that my average energy will be given by the negative of the partial of the natural log of the system partition function. Right, this is where we're going to deviate a little bit. So basically all I've done is written portion of this equation down here. Now if I'm interested in knowing it in terms of temperature, then I need to take the partial derivative with respect to the temperature. And I'm going to hold N and V constant. Okay? Now if I want this to be an equality similar to this, I need to multiply this by another differential. That will be D, N, and V. All right, so help me out. In order to make this statement equivalent to this statement, and I have a T dt here, what do I have to have in the numerator? dt, and then the denominator? d beta. Does that make sense? So I'm just doing a quick substitution. Okay? All right, and what it basically says is I need to know what dt d beta is in order to make this equality true. Right? So we can go back to our definition of beta. So I'm going to start here. d beta dt, that's the same as d 1 over kb t dt. Kb is a constant, so that comes out front. So I'm going to have 1 over kb. And then I just need to know the derivative of t to the minus 1. And what is the derivative of t to the minus 1? Minus 1 over t squared, or t to the minus 2. Make sense? All right. So this is the same as d beta dt. Now I'm interested in dt d beta. And so that's going to be minus kb t squared. Okay? All right, so that can get plugged into this. And what I can say overall is that my energy will now be minus kbt squared with a minus in front of it. That goes positive. So then I have plus kb t squared partial ln q with respect to t holding n and v constant. Okay? So this is going to be the same expression as above. It's just we choose one whenever we want to work in temperature domain, while you choose the other one when we want to work in the domain of beta, right? And you'll choose the domain that makes the mathematics easiest, okay? All right, so now what we're going to do is a little bit of an application of this. So basically what we've demonstrated is that if we know what this partition function is, then we can calculate the average energy. So we're going to look explicitly at a monoatomic ideal gas in its ground electronic state, right? And if you think back to when we talked about particles in chapter 1, the only energy that's available to our monoatomic ideal gas, if it's in its ground electronic state, are translational energies. Okay? All right, so we're telling you, and we will show where this comes from in a not too distant future, the system partition function is related to the particle partition function by the number of particles. So it's little q to the n over n factorial, all right? So this is how our system partition function is determined by the particle partition functions, okay? The other thing is, for this particular setup, a monoatomic ideal gas, this molecular or particle partition function is given by this equation. So this is an analytical expression, all right? And we'll show where this comes from in the next chapter. But when you look at this, you may recognize that looks like it's related to the particle in the box. Okay? And that's because it is related to the particle in the box. Right? And of course, what we're interested in is determining the energy of our system. So that means we need to take the natural log of the system partition function and then take the derivative with respect to beta. So now we're going to introduce some arithmetic tricks that we're going to use. All right? So this is the same as the natural log of the system partition function. All right? And then using some of the properties of the natural log, I can separate the numerator and the denominator. That'll be the natural log of the numerator minus that, the natural log of the denominator. All right? And because I'm going q to the n, that means I can pull that n out in front. Right? So that's going to be the same as n ln q minus ln n factorial. Okay? All right, so I want to do a quick foreshadowing. In order for me to get from here to the energy, I'm going to have to take the derivative of this side with respect to beta. This is a function of beta, right? It's a function of beta. This is not a function of beta. So if I take the derivative of this with respect to beta, what happens to it? It goes to 0. All right? And so basically what that says is I want to take my formula and manipulate it to isolate the beta portion of it from the rest of it. Okay? So now what I'm going to do is I'm going to focus on the particle partition function, and I'm going to pull beta out in front. All right? So that's going to be 1 over beta to the 3/2 times 2 pi m over h squared 3/2 v. Okay? All right, so this needs to get plugged into this value of q. All right? And what we recognize is that this is a product. Right? And so that means I can take the natural log of this portion plus the natural log of the rest of it. Okay? All right, so this is going to be the same as n ln 1 over beta to the 3/2 plus n ln 2 pi m over h squared 3/2 times the volume, and then minus my natural log of n factorial. Okay? Does that make sense? All right. So I'm going to rewrite this as, I can pull that 3/2 out front. 3/2 n ln. Now if I want this to be the natural log of beta, what do I need to do? So I'm natural log of 1 over beta. So to get to natural log of beta, I need to put a negative sign out front. Okay? Okay? And then the rest of this, I'm going to lump that all together. And I'm going to say this is a function that doesn't have beta in it. Okay? All right? So again, this is the natural log of our system partition function that I've just rewritten to emphasize the portion that has beta in it. All right? I take the derivative of both sides of this with respect to beta. What happens to the derivative of this? That goes to 0. Okay? So let me just write that explicitly. The derivative of f of no beta with respect to beta is equal to 0. All right? And that really says that all I need to take a derivative of then is what's left behind. And that's going to be minus 3/2 n ln beta. All right? So I'm taking the derivative of this function, 3/2 n, and the minus sign, those are all constants. They can come out front. That's going to become plus 3/2 n. And that means the only thing I have left to do is take the derivative of the natural log of beta with respect to beta. And what's that going to be? That's going to be 1 over beta. Okay? All right, and then at this point, what I can do is say, oh, I know that beta is 1 over kBt, so I can say this in turn is equal to 3/2 n kBt. Okay? All right, now I'm going to take this one step further, and I'm going to say, let's assume that we have 1 mole. 1 mole. If I have 1 mole, n is now going to be equal to Avogadro's number. And then we can say that the average energy is going to be 3/2 Na kBt. And what is Avogadro's number times the Boltzmann factor, or Boltzmann constant? That's R, all right? 3/2 RT. Right. Now, I don't know if you remember this, but way back in general chemistry, when you were introduced to the kinetic molecular theory of gases, you were told that the kinetic energy, the average kinetic energy of the particles, were 3/2 RT, right? And we've demonstrated where that comes from now, okay? All right, and that's going to be due to translations, because those are the only energies that are available to a monoatomic ideal gas. Okay? All right. And then what we're going to do is we're going to propose that this average value that we've just determined is going to be the same as what we expect to experimentally measure. All right? So that's experimental total energy. Okay? All right, and again, when we use the E, that means that we're using our ensemble. And when we see U, that's the macroscopic measured value that you've seen before. Your textbook doesn't use the term, but this corresponds to 177, 178 internal energy. Okay? All right, this leads us to a fundamental postulate of physical chemistry that I'll write in a moment, but I'll just explain at the outset. So basically what we're saying is that if we have the Boltzmann factor and use it to create probabilities using the partition function, the average value that we calculate is what we expect to observe experimentally. Okay? So this links the microscopic domain, quantum mechanics, to macroscopic classical thermodynamics. So we'll say properties calculated using Boltzmann factor and partition functions and here I'm going to add something in parentheses. we've shown previously, and we mentioned at the outset, if I use the Boltzmann factor and the partition function, those together give me the probability of being in a particular quantum state. So this basically says using probabilities of systems in ensembles yields macroscopic thermodynamic properties. Okay? Any questions about anything we've covered so far? Right? So I want to go through another quick example, and then we're going to give you guys an opportunity to work an example on your own. Right? So in this case, what we want to do is extend what we've done now to a diatomic molecule. Right? So up to now, we've just talked about a monoatomic ideal gas particle. So this is going to assume rigid rotor and the harmonic oscillator models. And we want to know the same thing that we've asked previously: what's the energy that we expect to observe? Okay? So again, we're going to start with our system partition function, written in terms of our particle partition function. In this case, our system partition or our particle partition function is a little bit more complicated. All right? Now you may recognize this portion is identical to what we've shown for the monoatomic ideal gas. Right? And so what energies is this going to be related to? That's going to be translational energies. All right? And then we see that we have two other terms here. One's got the moment of inertia in it, and the other's got h nu, where nu is the fundamental frequency. So this term with the fundamental frequency then is going to be associated with what energies? That's the vibrational energies. And the moment of inertia was associated with rotations. Okay? All right, so at the end of this, we're going to expect that when we talk about our average energy for our system of diatomic molecules, there'll be a contribution from translation, vibration, and rotation. Okay? All right, so keeping in mind that what we're looking for is the derivative of the natural log of the partition function with respect to beta, we start again with our system partition function in terms of the particle partition function. Because we know that we need to take the derivative with respect to beta, I'm going to take our partition function, I'm going to tease out all the portions of it. So beta, beta, and then this whole thing has beta in it. All right? And I'm going to pull those out to the front. All right? And then everything left behind, there's no beta in it. Okay? So no beta. All right, so now what I can do is I can take this whole thing, substitute into the natural log, and then I can say, well, I've got the natural log of the first term plus the natural log of the next portion plus the natural log of the next portion. Right? All right, so let's talk out this next portion real quickly. So this one's really straightforward. This is going to be minus 3/2 natural log of beta. This will be minus the natural log of beta. That all makes sense. Now I've got a numerator over denominator. So I've got the natural log of the numerator, natural log and exponential, inverse functions of each other. So I'm left with beta h nu over 2. Okay? And then the denominator, that's going to be natural log of the denominator. And then I've got the natural log of everything else, and that's going to be terms without beta in it. Okay? All right, so again, just to keep things in perspective, this is going to be translational. This is going to be rotational. Now what we see is that we've taken the vibrational term and broken it into two parts. And you notice that one part has got h nu over 2 in it. Does anybody remember what h nu over 2 is? It's the 0 point vibrational level, right? Remember we said it wasn't equal to 0. That's our 0 point. All right? And that means that this refers to the energy, the vibrational energies above that 0 point. Okay? All right, and we'll come back to that in a little bit. All right, at this point, what we can do now is we can take this system, or the particle partition function, plug that in to our system partition function, and that gives me all these separate terms. Okay? All right, and then next up, I take the derivative with respect to beta. All right, so the derivative of the first term with respect to beta, I've got the constant minus 3/2 n, and then the derivative of natural log of beta with respect to beta. The next one, it's going to be n over beta. In this case, this is a constant times beta. d beta is equal to 1. That becomes nh nu over 2. Right? And then here, I have to take the derivative of the natural log. Let's go ahead and do that. d ln 1 minus e to the minus beta h nu with respect to beta. All right. Well, we know that's going to give us the reciprocal, 1 over 1 minus e to the minus beta h nu. And then I have to take the derivative of this with respect to beta. So that's going to be times minus e to the minus beta h nu. And then finally, I need to take the derivative of this with respect to beta, and that's going to give me minus h nu. All right? And if we put that all together, that gives me nh nu exponential over this function. We good? Okay. Okay, so at this point, we're pretty close. The only difference between the partial of the natural log of the partition function with respect to beta and our energy is a negative sign. So that means I need to just multiply through by minus 1, right? And then at this point, what I can do is I can say, well, now it's time for me to put the temperature back in there. So I'll put NAKBT, NAKBT, and then we'll leave this in terms of the frequency space. Okay? This gets converted to RT per mole, or 3/2 RT. There we have RT, all right? And then just putting it all together, translational energy. What kind of energy is this? That's rotational. This is our 0 point vibrational, and then this is the energy above the 0 point. So that will be U trans per mole plus U rotation per mole plus U 0 point vibration plus U for vibration. Okay? Does that make sense? All right, so what I want to do now, everything we've talked about up to this point is going to be covered on the exam, and now I want to give you a chance to apply it a little bit. So you can work in groups of up to 4, right? There should be 2 sides. Let's start with the side that's asking you to calculate the average energy for a monoatomic ideal gas in 1 dimension. All right, and because I know I can do these, I really want you guys to work them through as a group. All right, I can answer questions. Brian can answer questions. And part of your attendance score will be in determining the right answers too. Okay. So again, you guys can work in groups. Just make sure everybody's name's on it. Do you guys need any more? Oh, you can skip that one. So the question asks you for the heat capacity. We haven't got there yet. All right, we'll do that next time.
How do you get it? Is that 1 over RT? What is it representing in the formula? Like 1 over RT? Yeah, KB. Yeah, but what is it represented by other components? I'm not sure. I just know that maybe the outside is
All right, very quick question. Why do you think I'm asking you to do this today? I would say there's a 99.9% chance that there's going to be similar problems. Okay? Yeah. Is my beta wrong? Let me verify. 6.9 times. Oh, yeah, it is. It is. I forgot to take the reciprocal. What was that? But if you calculate it on the wrong beta, that's fine. 1.45. Is that what you got for your beta? 1.45 times 10 to the 21st. Yeah. Okay. Yeah. Yes. Yeah. Although I will say that the one that I'm going to post online isn't in terms of beta, but it's over 1 over kBT. But it's all the same other than that. Okay. Yeah. I don't want to go through and... Well, I guess I could. So I may do 2 versions. Okay. All right. All right, so the other thing I wanted to mention at this point, if you look at the partition function that you calculated, 0.0682, if that's what you ended up with, that's what I ended up with. If you calculate that with or without that last energy level, E4, there's no difference, okay? And so the reason I'm bringing this up is that energy is so high for this temperature that it has a low probability of being populated by a system. And if there's 0 to no probability of being in a particular quantum state, you don't need to worry about it when you go to do the statistics. It's like if you flip a coin, you expect a high probability of a head and a high probability of a tail. Now there may be a case where you might end up on the edge of the coin, but that's such a vanishingly low probability, you don't have to take it into account. Does that make sense? Okay. All right, if you guys are finished, I'm done. If you're not, keep working. And then I have, if anybody needs their homeworks 1 through 3, I'll read the names off real quickly again. Calfan Alrem, Alremeit. And Brian, if you could collect them, that would be great. Margaret Fernando, Ali Hussein, Noella. All right, other than that? Yeah, perfect.